today we're going to actually take integrals in the traditional sense using the fundamental theorem of calculus. But before we start, we're going to do kind of like we did last time. This is an integral that we can evaluate using a formula from geometry. Okay, so we're going to draw a little picture of this thing. Okay, 2 is up here. 1 to 4. Okay, well, y equals 2 is, that didn't look good. That'll do. Is the horizontal line, and if we're trying to find the area underneath that from 1 to 4, we can say that's a rectangle. And that area is going to be 3 times 2 is equal to 6. And then underneath, we did this last unit. We know how to find an antiderivative for x to the 4th minus sine x. Okay, what's an antiderivative for x to the 4th? 1/5 x to the 5th, yes. And then for negative sine would be positive cosine, because when we take the derivative of positive cosine, we get negative sine. And then what else? Yeah, it's plus c. You don't want to forget that plus c. Okay. I think that I mentioned last time, but I certainly wouldn't be bad to mention it again, that this is a definite integral. It's a number. The value of a definite integral is a number. It's an amount of area underneath a curve. And below, this is an indefinite integral. It defines a family of functions that are an antiderivative for the integrand. And then the question is, why are we using that same integral sign for both problems, right? They seem very distinct. Right? We've got, on one hand, we've got an area that we were evaluating using geometry. On the other hand, we were taking an antiderivative. They seem very disconnected. And the connection between the two is the fundamental theorem of calculus. All right. Mr. Messner had to get away from you kids, so he drove on I-35 at a velocity of 70 miles an hour for 2 hours. He traveled from mile marker 234 to mile marker 374. How could we figure out how far he traveled? And I'll just start out by telling you there's 2 ways, and their equivalence is basically the fundamental theorem. Okay, so what would be one way to find the distance he traveled? Subtraction. Okay, that was not what they did first in yesterday's section, but that's fine. Right? Yeah, if you went to 374 from 234, we could say that displacement or final position minus initial position is going to equal 374 minus 234, which is going to be 140. What's the other way that I could do this? Yeah, okay, velocity times time. We know that distance is equal to velocity times time from maybe physics or middle school science or who knows. And, you know, in just case you forgot, if you're supposed to multiply, divide, add something, remember, if you're starting out with 70 miles per hour, and you drive for 2 hours, right, that's going to end up being 70 times 2 is 140 miles. Yes. Thank you, Miss Colmia. Chemistry, 12th grade, you know. Taught me how to do that. I think that was the most valuable thing I learned in chemistry, even more so than the chemicals. I mean, I'm not a chemist, so. Yeah, the unit conversion, very useful. Okay, so let's kind of think about this in terms of calculus. On one hand, this 70 miles an hour for 2 hours, if we had a graph of velocity versus time, that would be 70, and this would be from time t equals 1 to time t equals 2. This is really what we did. We found the area underneath this graph. Oh, 0 to 2? Oh, yeah. I think I was thinking about that example I did before the quiz. Or maybe one that was on the quiz. And so then I find the area and it's 140. Okay, so on one hand we've got this area. But how is position, which is, we've got x2 minus x1, how is position related to velocity? What is position to velocity? Yeah, it's the antiderivative. So somehow this area and antiderivative thing is connected. Now I'm going to tell you, I'm not going to prove the fundamental theorem for you today. That's going to be a separate video. And we're actually going to spend the entirety of the next unit investigating the meaning of the fundamental theorem in terms of accumulation and rates of change and real life problems. But for now, you're just going to want to kind of remember how to take an integral. That's where we are. We're kind of at the building the skills step. And then we'll make the jump to the analysis in the next unit. Okay, so the fundamental theorem of calculus, probably also known as how to actually take an integral. Okay. So how we do it is, first we're going to find an antiderivative for our integrand, and then we're going to plug in the bounds of integration, the a and the b, and then we're going to subtract. Okay, it's a three-step process. And probably within a week, it's going to just be second nature to you. Okay, so let's take a step back to that first integral that we took right at the very beginning. We took it using geometry, an area formula. And now I'll tell you, even until the end of this course, integrals like this, I'm going to recommend you think of them in terms of geometry rather than anti-differentiating. It's fine. What we are definitely expecting is we're expecting this area to come back 6. Okay, so we're going to follow the three-step process. What is an antiderivative for 2? 2x plus c. Sure, I'll do that. And then what I'm going to do is I'm going to say I'm going to evaluate this between 1 and 4. The net change in this between. All right, so I'm going to plug in 4 for x. So 2 times 4 plus c minus 2 times 1 plus c, which is equal to 8 plus c minus 2 minus c. And notice here that this is going to be 8 minus 2 is 6. And the c's are going to cancel. And so when I take a definite integral like this, I'm not going to be including the plus c. Okay? Now you certainly can, especially if you're like the type of person that's prone to forgetting their plus c. But over time, you're going to stop doing that, and therefore, I recommend just stopping now. So that came out like we expected. Okay, here's another one that we can do using a geometry formula. And now this one could maybe go either way, depending on how you see it. Later on, if you had to do this integral, maybe you think about it as a triangle. Maybe you just anti-differentiate, plug in top and bottom, and subtract. Okay, so this is going to be 10 here. Since it's y equals x, this will also be 10. And so when we go to take the area, we're expecting this area to come back as, well, 1/2 times 10 would be 50. All right, so I hope that happens when I anti-differentiate, plug in 0, plug in 10, and subtract. Okay, so I'm going to anti-differentiate x, and an antiderivative for x would be 1/2 x squared. And then I'm going to evaluate that between 0 and 10. And some people in the peanut gallery asking me for my plus c, but I'm not going to be including them on this one. And so that's going to be 1/2 of 10 squared minus 1/2 of 0 squared. And so that's half of 100 is 50 minus 0 is 50. So again, it's working. This is great. Okay, here's a couple for y'all to try on your own. Okay, I'm going to freeze the screen. If you're watching at home, I would recommend you pause the video and work along, work yourself, and then check your answer against mine. Because in about 10 seconds, it's just going to flash up with the answer. Okay, here we go. All right, so that area under the graph of x squared plus 1, that is an area beneath a kind of a curved segment. And that was a big deal when they discovered that connection, how to do that quickly. Because, up to that point, probably pi r squared was, was the greatest thing ever. And they were really interested in finding, areas under curves. And then I also find it really interesting that the area under, one of those lumps of the graph of sine is an integer. That's interesting. Now, that only works when you graph sine in radians. Okay? Like, you do that in degrees, you're not going to get an integer. But that's not something that we're going to do in this course. Maybe one day and just when we have random time after lunch or something. We'll do that one. All right, next we're going to find the area enclosed by the graphs of these four equations. Okay, so the first thing when you just start given a bunch of equations and you want the area enclosed by them, you got to draw a picture. So here I am, I'm drawing xy plane. 3x squared plus 1. Well, there's 1. 3x squared is pretty steep. Here we go. X equals 0. That is right here. It's the y-axis. X equals 2. I'll just make that maybe like right here. And y equals 0. That's over here. That's the x-axis. So really what we're looking for is the area of the highlighted region. So what we're going to do, kind of like what we did on that quiz y'all just took, is we're going to set up an integral for this, and then we're going to take it. Okay, so the integral is going to be the area under the graph of y equals 3x squared plus 1 between x equals 0 and x equals 2. So we're going to find an antiderivative. What would be an antiderivative for 3x squared? X cubed. And then what about 1? Okay, yeah, for some reason that gave them a lot of problems last year, the antiderivative of 1. They would try to say it was 0. And then we're going to plug in 0, and we're going to plug in 2. Okay, so that's going to equal 2 to the third is 8 plus 2 minus 0 plus 0. Okay, so that's going to be 10. That's a problem we can do. Here we've got kind of a different kind of problem. We're going to solve for one of the bounds of integration when we know what the area is. So I'm going to have y'all find the value of k. I think that this is something, it might be a little challenging, but it's something you could definitely do using the three-step process that we have right now. Okay, so I'm going to freeze the screen. If you're watching at home, pause the video. The answers will be coming up soon. All right, here it is. So we anti-differentiated 3x squared, and we got x to the third. We said that the difference in x to the third between 2 and k was 12, so k to the third minus 2 to the third equals 12. Meaning k to the third minus 8 is 12, so k to the third is 20. And if k to the third is 20, then k to the 1 is 20 to the 1/3. And 20 to the 1/3 is the third root of 20. So that was, maybe a challenging question, but something that's right at y'all's level right now. All right, here we're given a table of data, and we're asked to find some integrals. All right, so I'm going to start with the one in red, the integral from 1 to 3 of f prime of x dx. Well, that's interesting. What would be an antiderivative for f prime of x? F. Yeah, so f prime is the derivative of f. So the antiderivative of the derivative is going to be the original. So what I'm going to do is I've found an antiderivative for f prime. That's f of x. We're going to evaluate that from 1 to 3. And that means I'm going to have f of 3 minus f of 1. And those are pieces of data from the table. Here's f of 3 and there's f of 1. So that's going to be negative 4 minus, oh no, that's not f of 1. That's f of 1. Negative 4 minus 5 is negative 9. Okay, y'all do the integral from 0 to 4 of f prime of x. It's the net change in f between 0 and 4. And now the one in green, kind of have another point I want to make there. Last time I told you that, well, if we're kind of going backwards, if we're integrating backwards from 3 to 2, it's going to be the opposite of what we get if we integrate from 2 to 3. And I explained it in terms of the Riemann sum. Delta x would be negative each time. But I really like this in terms of the fundamental theorem. Okay, so what I'm going to do is I'm going to, I know an antiderivative for f prime. That's f of x. I think I've convinced you of that. And we're going to plug in 3 and 2. So this is f of 2 minus f of 3. But then notice that f of 2 minus f of 3 is the negative of f of 3 minus f of 2. So you can see that if you reverse the bounds of integration, once you get that antiderivative, you're going to end up with the opposite difference. So you'll just have the negative of what you would otherwise. So f of 2 minus f of 3 is going to be 2 minus negative 4 is negative 6. And now the one in pink, I want you all to do that one. It's, positive 6, excuse me. Whoops. Yes, 2 minus negative 4 is definitely positive 6. All right, so y'all do the one in pink. If we're getting home, do this one on your own. Answer's coming up in a couple seconds. All right, here you go. I split the integral into two separate integrals because for easy ones like integrating a constant, I really recommend looking at this as a geometry problem more so than a calculus problem. Now, if you wanted to, you could have certainly cooked up an antiderivative for this and said it was 2x minus f of x and evaluated that from 1 to 2. But you could have potentially gotten lost in subtraction or arithmetic, made an error or something. I wouldn't want that. So my recommendation on these is to just do it as a rectangle if you see it that way. And if you just want to do it with antiderivatives, feel free. Just get it right, All right, so the last one I've got is a multiple choice question. And it even comes with a hint to use a trig identity. And so remember that everyone knows that cosine squared x plus sine squared x equals 1. But that doesn't have anything to do with tangent squared. So what I'm going to do is I'm going to divide everything by cosine squared x. So that's going to be 1 plus tangent squared x equals 1 over cosine squared x is secant squared x. So tangent squared x is equal to secant squared x minus 1. All right, so I'm going to rewrite this integral. You too. Okay, an antiderivative for secant squared is tangent x. And an antiderivative for x, 1 is negative x. And I'm going to plug in 0 and pi over 4. So this is tangent of pi over 4 minus pi over 4 minus tangent of 0 minus 0. All right, tangent pi over 4 is 1, so I have 1 minus pi over 4. Minus tangent of 0 is 0, so 0 minus 0. And I've got 1 minus pi over 4.